In exercise 11J, we look at another rule for approximating the area under a curve. This rule is new. You haven't seen this formula before. It's called Simpson's rule. However, interestingly, the rule is always covered in the general course. So the fact that general students have been exposed to this formula for calculating area should be an indication to you that it's not that difficult a formula, but it is new. One more thing that I would point out about both the trapezoidal rule and Simpson's rule is that there's almost always a question testing one or the other. So in a formal assessment task, you could expect a question that will be on one of these two rules, as well as your calculus questions about calculating area. So please be aware of it. You'll need to know both and expect a question on one of them. You'll know that I've given you the link to the website with the trial exams from the private schools. If you flick through any one of those, you will find a question either asking you to calculate the area using Simpson's rule or trapezoidal rule. And you could, once you've done these two exercises, you will be able to go back and have a look at some of those questions. Okay, what is this Simpson's rule? Well, again, I think I'll take a blank sheet and I'll talk about it from there. So you can see here that I have sketched a function, just drawn this function, and I've tried to reproduce it over here. In this first diagram, I've used one application of Simpson's rule, and over here I've got an example of two applications under the same similar function, but now two applications. So in one application, we actually need three function values. So you need your limits from A to B, and that's not surprising. But in Simpson's rule, we have to know the middle x value between our two limits. We also have to know the function value, the height of this function at this point. The rule then becomes, and we also need, because this is exactly in the middle, we call the distance between our first limit and the middle, we call that h, and obviously exactly the same distance between the middle, well, otherwise it wouldn't be the middle, and our second limit. The rule then becomes that the area is approximately equal to h on 3, so you've got to know that, 3. It's the first function value, so it's this distance, this length, this height, however you like to think of it, and 4 times the middle function value, 4 times this height, and then, oops, that should be function at B, then this height. So that is the rule. Simpson's rule does appear on the reference sheet. It doesn't look like the rule as I've just written it. To me, it looks quite complicated. It talks about a 6 here, and I guess that comes from our h being b minus a on 2. B minus A and halve it, and all of that had to be divided by 3, so times a third divided by 3. So because it's h on 3, so that's where your B minus A on 6 comes from. First function value, we've got that last function value, and 4 times the function value in the middle. That just seems like a bit of a complicated way to write it. It's there on the reference sheet in that format if you don't have any issue with it. Otherwise, I just strongly encourage you to think about this diagram here, and yeah, the simpler form of Simpson's rule, where it's these distances between our values divided by 3, first function value, 4 times the middle, and last function value. When we go on, and obviously you can imagine now they're going to require you to do more than one application. For say 2 applications, you can see I've gone from A to B, but this time we need to fit in exactly 2 applications, so I divided that region in half. We needed a middle value for 1 application and the middle value for the next application. That then gives us 1, 2, 3, 4, 5 function values in all, and we just use the rule in the format we saw it back here in 1 application, and H would be a much smaller value this time. H is the distance between our function values. H is the distance between your function values. So we could write here our area is approximately equal to H on 3. Now, if I call this f of A, and then this is f of first function value, second function value, third function value, and then f of B, then you'll let me do it the long way. So you can see there I've written it up, and I'd mentioned in a previous video that maths is all about recognising patterns. We're going to see a nice, interesting pattern occur here when we use Simpson's rule. So, like I said, I'll just step you through it from the beginning. So, considering this as my first application, I've got H on 3, the function at A, 4 times the function at x1, the middle function in this first application, and the function at x2. And the second application, now I'm doubling up on this function at x2. I'm using that value again. I'm using, then, so it's one of those. It's 4 times the middle function, which I've called function x3 and f of b. From there, I'm taking out the h on 3 from these 2 terms, and we've got it's equal to, so we've got f of a, 4 times f of x1 and f of x2. And then out of here, we've got another function at x2, 4 times the function at x3 and f of b. Let's take a little minute to look at this last line that I've written here. We've got function at a and function of b. We've got 4 times the function at x1 and no more of those. The function value of x1 doesn't appear anywhere else. We do have, though, another 4, and that is 4 times the function value at x3. So there's 4 times the function value at x1 and 4 times the function value at x3. And we do end up with 2 lots of the function value at x2. Let me write that up and show you then what that looks like. So you can see I've chosen to put it in this order, h on 3, function a and function b at the front, because they only occur once. I've taken the common 4 out of function x1 and function x3. Now, one more thing, you will often see in various textbooks, or you'll hear various teachers talk about these as the odd function, only because 1 and 3 are odd. the first two odd functions. So the function value, the first odd position, which is 1, it's the first odd number, and then 3, those function values need to be multiplied by 4. Here, 2, you can see, is an even number, and we want 2 times the function value at the even x value position. Now that pattern continues in that format for 3 applications, 4 applications, etc. It's always h on 3, first function value, last function value, and 4 times function values at any odd position, and 2 times function values at every even position. And like with so many new things, that might take you a little bit of time to get your head around. You might want to rewind. You might want to write these out yourself. The important thing is that you can understand this situation, and certainly if you're having any trouble, please don't hesitate to ask me about it.